Welcome to this little tutorial on inverse transform sampling. This is a very efficient sampling algorithm provided certain conditions are satisfied. In this tutorial, I am going to explain this algorithm, but before that, you should know that this algorithm is known by many other names. One other famous name is inverse CDF transform, and yet one more name is Smirnov transform, named after a great Russian statistician. That said, the trick to understand this algorithm primarily hinges on your understanding of CDF. And it is so important that I am spending 2 to 3 minutes explaining what cumulative distribution function or CDF is. Let's start with the probability distribution function that is defined as this. Essentially an exponential distribution which is valid only for x greater than or equal to 0. And here is how its plot would look like. One of the ways we use density function is to ask it for the probability of an interval. For example, here I am asking what is the probability that x lies between 1 and 3. And this translates into computing an integral or area under the curve as shown in the plot. So we can further expand it into the integral that would look like this. Since I have picked a very simple univariate density function, I can easily integrate it. But most of the time, we would like to avoid the integral. And one general approach to get around it is by finding a function whose value would provide us the same answer as we would have obtained by doing the integration. And this is where CDF or cumulative distribution function has a role to play. As such, the notion of CDF applies to both discrete and continuous random variables. So here in this case, I have applied to the continuous random variable as an example, and it represents the probability that the random variable is less than or equal to some number indicated using a small x here. Now, even though it is written like this, really what you should see in your mind is that the probability that a random number lies between negative infinity and small x. Generally, the convention is to just not write the negative infinity part. And I have already showed you an example of area under the curve. So this would translate into an integral as well, but it would now be from negative infinity to x. And for our function, that is f of x, we know that it is 0 for x less than 0. So if we split our integral into two parts or two terms, then we can simplify it. Essentially, we will get rid of the first term, and this is how it looks simplified. Now I'm going to solve this integral symbolically using a dummy variable t, and the result would be 1 minus exponential of negative x. And this is the CDF for our given PDF. Now I will prove to you that we can obtain the same result as we got earlier when I integrated it manually. Here I have written the problem in a bit different manner, but you should see that it is still valid. Essentially, the area under the curve can be computed by first computing the probability between infinity and 3, negative infinity and 3, and then subtracting the probability between negative infinity and 1. Which, by the way, is same as saying the cumulative of distribution of x and can be written like this. Now it is simply a matter of writing a functional form of our CDF, and we have solved it. You can appreciate that it is same as when I manually solved the integral for our problem. Let me plot the CDF as well. You should also note that getting probabilities using CDF is faster as you are now simply evaluating a function. Here I am showing you the visual of what I did earlier, and that is all you need to know about the CDF. And now we will talk about the inverse of CDF. Well, CDF is a function, so when we are talking about an inverse of a CDF, we are talking about inverse of a function. Visually, which means that we will pick a point on the y-axis and then hit our curve and then go down from that point to the x-axis. But computers are not going to do that. So let's see if we can get x from our function by by playing around with the equation that we have. Here all I have done is that I have moved the 1 to the left hand side, and so I've simply exchanged the left hand and the right hand side so that x can be on the left hand side. Now to remove the exponential, I'm going to use the logarithm, as I know that log of exponent will cancel each other, and this would lead to our final formulation. Good news is that for this problem, we do have an analytical inverse. That is, I have a function that given the value of y, I can get x. So far, so good. And now comes the moment to reveal the big idea behind this algorithm. If you notice, the min and max of the CDF is 0 and 1 respectively, which is also, by the way, the default support for a standard uniform distribution. Now, uniform distribution gives us random numbers that are equally likely. And the idea here is that we could use this inverse CDF to get the x. Essentially, we are trying to see the y-axis here in this plot as uniform distribution. Let me first show you the empirical results of doing this, and then we will talk about the proof of why this works. Because right now we have made an assumption that the y-axis, the points that we will get from the y-axis seems to come from uniform distribution. We have not proven it. We are just going to observe first the empirical results. So what I did was that I generated samples from the standard uniform distribution, and you should be able to see that these samples are creating the rectangle and showing that they are all equally likely. I then passed all these samples to the inverse CDF, the equation that we obtained in the previous screen, and the results would look like this. This essentially gave me the number of samples for each x, and then I made the histogram. And indeed, you can see that it is following our PDF. So the algorithm does work, but still I have not explained why this worked. What is the proof? And to explain that, I will take the help of a related concept called probability integral transform. This is coming directly from Wikipedia, and it says that random variable from any continuous distribution can be converted to standard uniform distribution. And this is also called universality of the uniform, a grand gesture for the mighty uniform distribution. But note that in our case, we intend to convert from uniform distribution to our random variable x. So in a way, we are thinking about this in the reverse, or as an inverse problem. And in many ways, if you look at this statement clipped from Wikipedia, it reflects this sentiment as well. Here it is describing our situation quite well and stating that if we have a CDF for random variable x, then the random variable y can be obtained using the CDF. And hence it is written as y equals f of x. And more importantly, this y is standard uniform distribution. And if you look at our plot, you would see it as well. On the x-axis, we have our random variable x. We have a CDF in the middle. And then on the y-axis, we have a range that goes from 0 to 1. So earlier I had said that y-axis seems to have the same range as standard uniform distribution, but this theorem is confirming that as well. And since this is the case, then simply computing the inverse of this function that is CDF should indeed give us x distributed according to our PDF. Now, saying all of this is okay, but where is the proof, my friend? Well, there is a proof as well. Fortunately, not a page-long proof, and just a simple arrangement and rearrangement that will lead to the proof. But let me do this proof one line at a time so that you can clearly see what is happening here. What we are really proving is that if we apply the CDF to a random variable, it results in a uniform distribution, shown using this statement. Now, here is a side information. CDF of a uniform distribution is equal to y. If you are not aware of it, then you can go verify it yourself and or read the documentation of the uniform distribution. So now we get to the proof. As I explained earlier, we write CDF of a random variable like this. Nothing should surprise you here if you know what CDF means. Now I have used our statement and substituted it here. You can see that I have replaced y with the f of x. Now all I have done is that I have taken the inverse on both sides, and now this looks like again a CDF. So I could just simply write it like this, and it should be obvious that f and f will cancel each other out, giving us y, which is something that we know for sure, which means indirectly we have proven our statement, which is that y is a function of x, where function f is a CDF of the random variable that you are passing to this function. And more importantly, y will be a uniform distribution. Because we have proven this, its inverse should also be true, which means that if we can get y, which is a uniform distribution, which is indeed very simple to get, then getting the random variable x, which is what we are interested in, is just a matter of taking the inverse CDF transform of the uniform distribution. This all being said, life would be wonderful if it was all this rosy. There are severe limitations of this method. First and foremost, you need a CDF for your density function, which is not easy for all distributions, especially when you are in a multi-dimensional realm. Then once you have a CDF, it is not sure that you would have an analytical inverse of it. So you would have to somehow maybe numerically approximate it. And the killer is that this requires that you are working with a normalized distribution. I'm saying this because most of the problems in Bayesian statistics are because you do not have a normalized distribution. So you cannot really apply this method when you are trying to sample from a posterior distribution. That said, it does not mean that there is no use of this method. There are enough situations where it would work, and you should indeed prefer this method if you are satisfying all the constraint, because it is more efficient than the other stochastic and inefficient algorithms like rejection sampling. And this brings us to the end of this little tutorial. I hope I was able to explain properly what inverse transform sampling is, and the proof is clear to you as well. That said, if you have questions and doubts, please feel free to ask them in comments, and I would try my best to clarify. And many thanks for the time that you spent here in this tutorial. And with that, bye bye for now, and see you in another But What Is tutorial.